Here we are again. Let's go with some ossification and homeostasis. So the word ossification literally means bone growth. Homeostasis is this is more of a physiology term, but I think it's really important for understanding anatomy of bones and our other structures. Homeostasis is that maintenance of a steady internal environment. And so when we talk about bone homeostasis, we're talking about um, its ability to maintain calcium levels and phosphate levels in the blood and store them in the bone or release them when necessary. So a little preview. Let's talk about ossification. Um, Ossification is the formation and development of bone and connective tissue. We have two patterns of ossification. We have intramembranous ossification. So that word intra means within. The word inter means between. The word inner with two N's means inside of. So this is intramembranous ossification, literally means within the membrane. So this develops from the mesenchyme, and it produces flat bones of the skull, some of our facial bones, our mandible, the central portion of our clavicle. We haven't gotten to those bones. Hopefully you've been studying them, but we haven't gotten to them just yet. And we want to contrast that with endochondral ossification. This begins with hyaline cartilage as a model or a template. And it produces most of the rest of the bones in the body, such as the upper and lower limb bones. So when we're talking about intramembranous ossification, the ossification centers form within thickened region of the mesenchyme. So again, we're making flat bone here. The ossification centers forms within that mesenchyme. We've got those osteoids. That's that substance that is being released, which is going to strengthen. And you've got collagen fibers, these mesenchymal cells, and your osteoblasts. Remember that osteoblasts, these are bone builders. So we have the center of this called the ossification center. The osteoid undergoes calcification, so that liquidy matrix starts to harden, and it's when we say it's calcified, that's that hard substance primarily made of calcium and phosphate that's going to surround the bone cells. The woven bone and surrounding periosteum form. So now you've got some of this bone being formed. This is a trabecula of the spongy bone. And you see this mesenchyme condensing to form the periosteum superficial to that. And then the lamellar bone replaces that woven bone as compact bone, and that spongy bone forms. So now we're getting that full bone. You've got the compact bone. Remember, we have compact bone on both sides of the spongy bone when we're talking the flat bones. And then you have that periosteum that layers around there. In endochondral ossification, we start with fetal hyaline. So the fetus, unborn baby, starts with hyaline, mostly cartilage, very flexible, strong, but flexible. And that serves as kind of a template or a model. The cartilage begins to calcify, and a periosteal bone collar forms. So you can see that happening right here. Primary ossification center forms in the diaphysis. So the bone starts to harden in that diaphysis shaft first. And then you have secondary ossification centers form in the epiphyses. And those are, remember, we have our epiphyseal plates. That's the area of bone growth. So bone replaces cartilage, except at the articular cartilage at the very ends of the bone is that articular cartilage. And then at the epiphyseal plates, which are continuing to grow and extend that bone lengthwise up until, mid-teenage years, late teenage years for males, a little earlier for females. And those epiphyseal plates eventually ossify and form epiphyseal lines. Now you can see that one's here and one up here. We talk about the zones of the epiphyseal plates. We have zone one is more deep. That's the zone of resting cartilage. You have the zone of proliferating cartilage. That means it's growing and getting bigger. Zone three is the hypertrophic cartilage. So hyper means lots of. Trophic is food. So this is kind of growing and actively growing. You have now a zone of calcified cartilage, which is hardening, and then that area of zone of ossification, which is now, I guess, officially bone. And you can see this epiphyseal plate here just at the end of this bone in your forearm where it meets the wrist. And you can see them also on your fingers. Remember, all the bones in our fingers are long bones. Actually, we'll talk about these more, but the bones in your wrists are actually short bones. So growth and repair. A long bone's growth is growth and length is called interstitial growth. That occurs at the epiphyseal plate. That bone grows in diameter is called oppositional growth or appositional growth. This occurs in the periosteum, where those osteoblasts lay down external circumferential lamellae, and osteoclasts enlarge the medullary cavity from within the bones. Remember, the blasts are building, the clasts are breaking down. They need to break down that area inside the bone in that hollow medulla so that the bone can expand its circumference, right? The round part, right, to get bigger. You can see an example of this going on here. The periosteum out here, just superficial to the compact bone. You have that medullary cavity, that hollow center. The bone is being broken down here, or we say reabsorbed or resorbed by the osteoclasts. They're breaking it down. Bone is being deposited in the outer rim by the osteoblasts. And so eventually you get that bone getting bigger and bigger and bigger in circumference. Continual production of new bone and reabsorption of old bone is called bone remodeling. This helps maintain calcium and phosphate levels. So that homeostasis we were talking about before, your body in many places needs calcium. It needs phosphate for muscles, for energy. And so we need to have a steady state of calcium and phosphate flowing through our blood so that any of our cells can use it at any time. And so if we have high levels of calcium and phosphate, they get stored in the bones. And when our calcium and phosphate levels in our blood drop, then we can harvest that calcium and phosphate from our bones. Those osteoclasts will break down the bone and release those nutrients, those minerals into the bloodstream. This can be stimulated by stress on the bones. And like I said, that can be a good thing and a bad thing. And as we age, this process begins to slow down. And so we really want to stress our bones in a healthy way. And that's why strength training, lifting heavy stuff in a safe way, puts that little stress on the bones and causes this calcium and phosphate to be absorbed into the bone to create stronger bones. If we just sit around all day, I don't know if you've ever, oh goodness, what is that movie called? Wall-E. You've seen the movie where the humans have just left Earth and are just sitting on chairs all day long, eating and watching their screens, they're not stressing their bones at all. They're actually in outer space. There's almost zero stress on their bones, and they kind of become blobs. And that would sort of be what happens to our bones. We would store less and less calcium and phosphate in our bones. Our bones would become soft. And so that leads us to breaks. And so actually one of number one, or not say number one, but one of the highest causes of death in elderly are bone breaks. And you break a bone, hip, femur, in old age, and that oftentimes leads to death. So let's consume lots of calcium and phosphate. Let's put healthy stress on our body, and let's live into old age with strong bones. Service announcement for the day. This occurs at different rates in different places in the body. So bone is highly vascularized. And that means that it has lots of blood vessels moving through it. So with lots of blood vessels means that there's lots of nutrients, right? So there are the nutrient artery and vein. They supply the diaphysis of the long bone. Usually just one nutrient artery and one vein per bone. They enter into the bone and they exit out of the bone. We also have metaphyseal arteries and veins. These supply the diaphyseal side of the epiphyseal plate. So that would be kind of, oh man, this is going to be rough. I'm going to draw this. So if this is our bone, and this is my epiphysis of the bone, and we have the epiphyseal plate going on here. Down here is the diaphysis, and up here is the epiphysis. This would be the diaphyseal side of the epiphyseal plate. Yes? All right. Okay. And then we have epiphyseal arteries. They supply the epiphyses, and the periosteal arteries supply blood to the external areas of the bone. Here you can see those blood supplies coming into the bone, highly innervated, highly vascularized structure. We talk about growth, maintenance, and repair. So hormones, vitamins, and exercise are all involved in this. Hormones, when we talk about the endocrine system, hormones are the chemical signals in our bodies that travel through our blood. Vitamins are chemicals that help our enzymes do their job, and then exercise is running around and lifting heavy stuff and getting out of breath. So hormones regulate bone cell activity and regulate calcium levels. So we have growth hormone, which is a hormone, and insulin-like growth factor, also a hormone. They stimulate cartilage growth at the epiphyseal plate. Thyroid hormone stimulates metabolic rate of osteoblasts. So that just means making those osteoblasts build faster, and that stimulates bone growth. Calcitonin and parathyroid hormone, they kind of have contrasting effects on each other. So if we think about homeostasis as maintaining a balanced environment, you can put like calcitonin on one side and parathyroid hormone on the other side. And so if a level system is the right amount of calcium in the blood, then if calcium deposits get so calcitonin, if we are low on calcium, then calcitonin, or I'm sorry, if we are high on calcium in our bloodstream, calcitonin will be released. It'll slow down the breakdown of bone, and it'll build more calcium deposits in our bone. If we have not enough calcium in our bloodstream, Then parathyroid is going to stimulate those osteoclasts to start breaking down bone and releasing that calcium back into the bloodstream. Thereby, they kind of maintain homeostasis in that way. And then our sex hormones, estrogen and testosterone, they're also part of this process. Vitamins are needed for normal bone growth and maintenance. Vitamin A helps to activate those osteoblasts. Vitamin C is required for collagen synthesis. That's to make those collagen fibers. And then vitamin D, it stimulates calcium absorption from the GI tract in the blood so that calcium is available for bone formation. If you recall back to our discussion on skin color and how the farther we live away from the equator, the less UV light there is. We need that UV light to help to build vitamin D and to make it available in our bloodstream. And so we need that. And that's why you may notice sometimes you have milk that is vitamin D fortified, especially for students who live way north. Mechanical stress is detected by osteocytes, communicated osteoblasts. It increases osteoblasts and activity and results in increased bone stress, bone density. So mechanical stresses that affect bone result from skeletal muscle contraction and gravitational forces. So that's something that we have to really think about with our astronauts who are in space for long periods of time. Bones of athletes actually become thicker and stronger as a result of repetitive stressful exercise. And that's really important. Jumping and running and lifting heavy stuff, that puts that healthy stress on our bones and it builds stronger bones. And that's good because as we get older, our bones lose mass with age, but we can slow that down with weight-bearing exercise. So start that now when you're young. And then when you get to be my age, hopefully you'll have stronger bones. Breaks. So we're going to go just real quickly through breaks in bones. All breaks in bones are called fractures. Don't say, oh, did you break it or did you just fracture it? They're all fractures, and they come in lots of different ways. Stress fractures, traumatic fractures, pathological fractures. They're named after the amount of soft tissue damage that's happened. Simple fractures, compound fractures. If you want to know all about fractures, read into this, and orthopedics is in your future. Healing from a fracture. So when you have a fracture, remember that the bone is highly vascularized. So a fracture is going to lead to breaks in the bloodstream. That's where lots of swelling occurs. A hematoma is lots of swelling that builds up. Eventually, fibrocollagenous callus forms. So you have this scar tissue building around here, essentially. And then a bony callus forms around that. You kind of get this little knob. You can even see that on an X-ray. And then eventually that bone, through the work of osteoclasts and osteoblasts, remodels itself. And it's actually one of the most amazing things about being a human or being an animal is that our tissues can heal themselves. It's pretty amazing. So in summary, we talked about bone growth ossification, talked about intramembranous ossification and skull, the flat bones of the skull, and then endochondral ossification of our other long bones. We talked about interstitial growth and appositional growth. And then we talked about some of those things that maintain homeostasis and promote good bone growth. So hopefully that was interesting and helpful. And see you next time for bone markings.